shall I share my screen then?
Yeah, sure. I mean,
Okay, I can start whenever you're ready.
all right. Yeah, sure. I think we're ready. So we'll have Kai SCHWENZER working, presenting us about the mergers of neutron stars. Thank you very much. Go ahead.
Okay, thanks a lot. So first of all, thanks a lot to the organizers for giving me the opportunity to present this here. And I was asked to give a very general talk on neutron star mergers. And so that's what I'm going to do. And I'll try to keep it rather basic because I saw that, well, a big fraction of the participants is actually undergrad students even. So that's why I want to keep it, well, keep the level of formulas and details to a minimum. And so the whole thing is kind of, well, the way the workshop is now done is kind of chronologically the wrong way. So this is what happens first. We had heard a lot of nice talks on, say, the electromagnetic signals that come later, some much later. And well, all that stems from this event, namely the merging of these two sources. And well, they can spiral each other for a long time, and eventually they merge. And that then typically happens very fast. And then the key feature that this does is it emits what's called gravitational waves. And so maybe also for the students, if you don't know what a gravitational wave is, a gravitational wave is basically like an electromagnetic wave, but it's not an electric field or a magnetic field that's oscillating, but it's space-time itself. That means distances in space-time will change. They will, say, shrink and expand as that gravitational wave goes through you. And so, well, somehow in the last decade, we finally were able to observe these gravitational waves first in binary black hole mergers, 2015, and then 2017, basically the first point that was possible, we saw with advanced LIGO the neutron star mergers. And well, that was a big success. And well, yeah, that event, I mean, we heard about it before, was kind of too good to be true because there were all kinds of nice signals, electromagnetic signals related to that. And obviously, correspondingly, not much later, people got a Nobel Prize, and this was a big thing. But this kind of started the age of gravitational wave astronomy. And so now we can hopefully in the future see many more of these events and understand them much better. So these discoveries were very important, but now we kind of have a new tool. I mean, say, gravitational wave astronomy is, well, an extension of the standard optical and electromagnetic astronomy that we used for centuries. And this will open a new window to the cosmos. And say, what I want to point out is that they're kind of complementary. So this is the frequency range here. And this is all the electromagnetic spectrum. It kind of goes down roughly to a kilohertz. I mean, below that, it will be very hard to still detect these signals because they're very low energy. And as you know, it goes arbitrarily high if you don't even consider particle rays. And the kilohertz range, that's exactly where kind of gravitational wave astronomy begins. And so that's really nice. And also this can then go down very low in frequency and thereby probing bigger and bigger and bigger objects. And the big difference is that electromagnetic radiation, as you know, is emitted by charges, and correspondingly, this is easily absorbed in matter because matter contains charges, and it's generally emitted from the surface of dense objects. And so that's what we see. If you see light, it comes from, well, the surface or maybe even the atmosphere of that object, but we cannot look inside. Gravitational waves are completely different. They are emitted by huge and quickly moving masses. They're hardly absorbed by matter. And correspondingly, they really probe the interior of dense objects. And talking about neutron stars, we want to know what's inside. And so that's nice. So these are the sources of gravitational waves and the corresponding detectors that might be able to see them. I mean, so far we are kind of here. These are these mergers. These are the ones that we actually saw so far, compact binaries in our galaxy and beyond. And these are the detectors, advanced LIGO, Virgo. These are all terrestrial detectors. I will say more about these. But well, you know, as I said, this is a large spectrum, and we could see all kinds of signals. I mean, we could see similar, even bigger black hole mergers. There might be rotating and oscillating compact objects or supernova, and all kinds of, or even quantum fluctuations from the early universe. And there are corresponding detectors or space-based say interferometers here, or in this range, even something called pulsar timing arrays, which basically use, well, pulsars themselves as, or as the light traveling, or the radiation traveling from these pulsars to us, and all the space in between as the detector to measure if a gravitational wave passed through. And this way you can obviously measure much larger distances and correspondingly much lower wavelength, much larger wavelengths, much lower frequencies. And yeah, so hopefully in the future we'll learn much more with gravitational wave astronomy. And another one is the cosmic microwave background polarization. I mean, this was a big thing a few years ago when people thought they already saw it. That unfortunately didn't turn out to be true, but the cosmic microwave background, which is purely electromagnetic, might store some imprint of these gravitational waves in the early universe. And that's also something that would be extremely exciting, that would hold true. Okay, and so the current sources, as we saw, everything we saw so far are binary mergers. And there are two source classes. They are black holes and neutron stars. And I will mainly talk about this. And the reason is, I mean, we saw many more of these already, black hole mergers. But the unfortunate thing, I mean, black holes are kind of boring objects, right? There's a no-hair theorem. So they only depend on a few parameters. I mean, this is nice. They're very clean signals. You can have a nice template and easy to find them. But well, you know, you might learn interesting lessons about gravity, but not about matter, because all the matter is hidden in here, and we just cannot see it. So that's a problem, and maybe something around it. But well, this is a much nicer thing to learn something about matter. And so we know in neutron stars, the interior consists of the densest form of matter in the cosmos, and well, it's very complicated, but very interesting. And gravitational waves would give us a way to actually probe the interior, to see inside, because they just go right through. I mean, they're emitted by the entire star, not just by the surface. And that makes the big difference why these are amazing probes to learn something about the interior. Okay, and so just to say a bit more about this, I mean, the interior is really complicated of neutron stars. Somehow, the more we go inside, the less we know about it. I mean, the outer part is kind of iron, and if you go further inside, they're heavier and heavier nuclei and so on. And somehow we understand this part pretty well, but the further we go inside, the more weird it gets, and there might be, say, these funny pasta faces here at the interface between where you still have nuclei, but they then already have weird shapes. And in the interior, we expect that there's some liquid of, well, stuff. But what that is, I mean, somehow in the outer parts, it might be neutrons. That's why it's called neutron star. There should be some neutrons. But if you go inside where the question mark is, we just don't know what it is. And there are really many, many possibilities. What could be there? And we would like to figure out, well, what's actually realized there. And the problem why this is so hard is that we know the underlying theory of matter. That's called quantum chromodynamics. And well, the theory is understood. What we cannot do is we cannot solve it at high density. And that's really unfortunate, because basically everywhere in all other regimes, this theory has by now been solved, and we have nice results. at high density, there's some problem that's called the sign problem, and that prevents us for nearly 50 years to solve the theory at all at high density. And so we don't know anything from first principles. What is realized there? That's why this question mark is still there, and that plot still holds, or this graph still holds. And so, as I said, so far no signals otherwise escape the opaque interior, say no electromagnetic signals. And so far all we know about them comes from far outside, say the surface or the magnetosphere. And then it's very indirect to kind of infer the signals that you have out there. I mean, these are very complicated objects, to then go back and guess what, say, signature that you can measure could be correlated with the interior. I mean, it's not impossible, but this is hard. And now these mergers, they would give us a way to actually, well, yeah, actually see inside. And so what could be inside, as I said, is really tricky. And the reason for this is, so we know this theory that describes matter is formulated in terms of quarks and gluons. The problem is we have never seen a single quark or a single gluon. So there's something called confinement, and all the matter comes in terms of other particles, baryons, nucleons, hyperons. I mean, there will be leptons in these stars. There will be resonances, maybe mesons, all kinds of particles could be there. And there's a whole slew of these particles, right? So as you go to high density, you go to high energy, and at high energy, there are more and more of these. And so there's really a lot of them that could actually be present in a neutron star. And all this is very sensitive to small details. What, you know, in a lab, we can kind of probe what the masses of these particles are, but their masses will change with density, and then their properties will change with density. And so even if the star is still hadronic, well, the properties of all these will be different. And it's really hard to predict because we don't have the theory to describe that. And so anything goes, basically. There could be all kinds of particles. We don't know which they are. And the same happens on the quark side. I mean, another possibility is that you have something called deconfinement. So at arbitrary high density, that theory predicts that there won't be any baryons anymore, neutrons, protons, and so on. There will only be these quarks and gluons, and they're kind of then not confined anymore. They're quasi-free. The problem is this theory predicts this only at arbitrary asymptotically large densities. I mean, if you really want to be on the safe side in a clean regime, this theory becomes kind of asymptotically free. That means at very high energies, very high densities, the interactions are not so relevant. Then you can solve the theory, and there we understand what's going on. But these densities are ridiculously big. And so in that regime, where neutron stars are based, say, a few times the density that you have in an atomic nucleus, or maybe 10 times, in this regime, we don't really know what's going on yet. And there are all kinds of interesting possibilities that could happen. And well, in this case, it's somehow simpler. You just have a few particles, these quarks, and in particular, at the densities in the neutron star, you can basically have three of them, the up, the down, and maybe a strange quark. So up and down is what makes up all the matter surrounding us, protons and neutrons. The strange quark is a bit heavier, but it should be present in a neutron star. The problem is, well, there are interactions between these quarks, and they can do all kinds of interesting things. And it has been shown that at very high density, you have something called color superconductivity, and the high, say, the asymptotic phase is something called a color flavor lock phase. That's where all these different quark flavors are fully paired. So this is similar to superfluidity or superconductivity. So they form Cooper pairs. They kind of are not. They don't propagate individually anymore, but they kind of form a condensate and kind of freeze out. I mean, you could think of this as, yeah, kind of frozen out. And say, if all these quarks are kind of frozen out and gapped, then you have this color flavor locked phase. But that's what you have at really high density. If you go to lower density, then somehow the interactions between them become more relevant. In particular, also the scales become more relevant. And the relevant scale in this case is the strange quark mass. The two light quarks, the up and the down quark, they are kind of, you can treat them basically as massless. I mean, at high density, they somehow, in a neutron star, they could still have a sizable mass, but at asymptotic density, they are kind of massless. Yet the strange quark is much heavier. And that's also, even in vacuum, has a sizable mass. And correspondingly, that's what controls what form of matter you form. The strange quark mass is kind of the driver that prevents this, say, if the strange quark mass becomes relevant, then this pairing here is disfavored. And then you get these partially gapped phases where only a few of them pair. And say the lower the densities you get, the more important the strange quark mass becomes, its size, the more weird phases you could get. And say in the limit, you would end up with no quarks being paired anymore. But in between, you can again have all kinds of complicated, inhomogeneous, anisotropic condensates. And well, you know, so far people just came up with a list of, oh, there could be this, there could be this, there could be this. But in principle, we have no idea how many phases there are. There could be literally hundreds of different phases of dense matter, potential phases. And well, a few of them are realized, right? So as you go up in density, there will then be a certain succession of phase transitions, maybe, and a certain number of phases that are realized at certain densities. But all the others are just not realized, and we don't know which of them exist at this point. So that's the problem. And so the hope is that doing astrophysics, we could figure out which of them is realized. If we cannot do it microscopically and solve the theory, maybe astrophysics give us the insight what is actually out there. And so to do this, there are kind of two different ways. I mean, you can look at static properties and say the static properties of matter that's described by the equation of state. And the problem there is that the equation of state is a very important function that describes, as I said, the static properties of any material. And it turns out that the equation of state can be rather similar for very different forms of matter. Okay. And now we have constraints from astrophysics that kind of narrow down the possibilities how all these different forms of matter could be. And within these constraints, well, there's a large restriction on the equation of states. And so no matter which of these phases you have, the parameter space is kind of restricted that, well, they are kind of similar. There's another way, namely to look at dynamic processes. And in this case, you have more. Well, matter has more you need more, say, properties to describe matter. And these are these so-called material properties like, I don't know, viscosities, conductivities, things like that. And they're determined by the low energy degrees of freedom of matter. And typically in a neutron star, matter is strongly degenerate, right? These are fermions. Neutrons, for instance, they form a Fermi sea. And so the relevant degrees of freedom are the degrees of freedom right at the surface of the Fermi sea. And depending on which form of matter you can have very different degrees of freedom there. And they can strongly alter these material properties, these dynamic properties, how your form of matter reacts to any dynamic process. And so these are some examples here. This would be dissipation in dense matter. And typically you get then some power law of certain quantities. This would be the shear viscosity. This is the bulk viscosity. And typically they all kind of have a power law dependence on the temperature. And if I say the temperature, this means temperature over the relevant scale of that object. In a neutron star, that would be the chemical potential. And that parameter T over mu in a neutron star is order 10 to the minus 4 or even smaller. The neutron star is a very cold object, a very dense object, and correspondingly this ratio is tiny. Now, if you have different power laws with respect to this, say this ratio, which is of order 10 to the minus 5 to 10 to the minus 4, and well, you have differences like 5 orders of magnitude here, this gives you 20 orders of magnitude difference in that particular property, okay? That means one form of matter might have a dramatic dissipation, the other basically has none at all. And so that's why these material properties can be more promising, because they can be very different if you look at different forms of matter. And so if we can describe such as dynamic processes that are dependent on these, it could be that even though there are lots of uncertainties involved, the differences between what we want to distinguish are so dramatic that we can nevertheless see it. And that's kind of the hope why such dynamic processes like a neutron star merger might be interesting to learn something about matter. Okay, so we already learned a lot about this in this, say, about the later stages. Well, binary merger, as I said, is an event where you have these stars spiraling in, they emit gravitational waves, they lose energy, they lose angular momentum, that's why they get closer, and over a long time, they will approach each other, and at some point, they smash into each other, basically at the speed of light. And as you can guess, this is a huge fireworks then that's going on there. And so we've seen this. So mergers, for instance, could be observable of neutron stars up to 300 megaparsecs. So we could see them out to really large distances. The problem is they are rather rare. I mean, somehow these neutron star mergers compared to black hole mergers are unfortunately rather rare. So we haven't seen many yet. And so far, as I said, we saw dozens or maybe 20 already by now, depends how you count, of black hole mergers, but also depending how you count 1 or 2 neutron star mergers. And so they're much harder to detect. They're smaller, you don't have that big masses, and the signal is less clean than the black holes, and therefore it's a bit harder to detect them. Okay, right, but the hope is that, well, once we have enough, that we can learn something. And such a neutron star merger typically has 3 different phases. And first you have the inspiral phase. I mean, that's what I said, that takes a long time. And I'll say more about this. This is a very characteristic signal. And so this is rather clean. The next phase is the merger phase. That's when they actually smash into each other. And what happens then depends strongly on the total mass of the progenitor objects, these 2 neutron stars. So if it's very, very low, then maybe a stable neutron star could emerge from that. If it's sufficiently high, and typically, I mean, so we don't know what the maximum mass of a neutron star could be. But if you take typical neutron star mergers and add, say, double them, then it's hard, you're already at a limit what a neutron star might have. And so it's not clear whether this can be possible. So the standard case would be that the mass is so high and it collapses to a black hole. And there are kind of also 2 different ways here, depending on how high the mass is. They could either collapse immediately into a black hole, and then you probably wouldn't expect much. Then the whole process, you will see the gravitational waves, but maybe not so much electromagnetic signals. But then at intermediate masses, you might have a metastable state of this neutron star, that it's not stable, but it's kind of stabilized by the angular momentum, right? These stars rotate around each other. There's a lot of orbital momentum, angular momentum, that will be taken over by this merger product, and it will rotate initially a lot, and that counteracts gravity. And can stabilize it for a certain time. And well, if thermal effects play a role, that might also help to stabilize it. And so this is kind of the generic case. That's probably also what happened in the one case we saw so far. That, well, yeah, this is stabilized for some time, for a certain interval, say typically dozens, maybe hundreds of milliseconds, and then it collapses. Okay. However, during that time, a lot happened, and even if in the end, say that the core of that merger region collapsed to a black hole, there's so much matter around it that we can get all these interesting signals that were discussed before. So, and finally, say once the merger then happened, this compact object will then typically still oscillate, right? It's still highly excited, and that's called the ring down phase. So in principle, you might see characteristic oscillations from that. The problem is all this is so messy, and it's kind of, well, it overlaps here. And so it's hard to see these signals. I mean, I'll get to that. This is what we actually saw so far, the in-spiral phase. We haven't observed any of these in gravitational waves or any other signal so far directly. So how can we see gravitational waves? And as I told you, gravitational waves are kind of, well, changing the distances in space and time. And so what we need to do is we need to measure distances as best as possible. And well, what people build is basically the best ruler ever, namely advanced LIGO. And this is an interferometer. It's 4 kilometers in length and has two arms, because gravitational waves are kind of typically quadrupolar in nature. They will stretch space in one direction, shrink it in the other direction. And so well, that's why it has this form that you can measure both. And so advanced LIGO consists of two such equal detectors on basically opposite sides of the US, one in Washington, one in Livingston, and one in Hanford. And so this way, somehow, as I'll say in a minute, there are huge uncertainties, right? We need to measure distances to ridiculous precision. And if we have two far apart, then you can kind of cross-correlate them and filter out some of that noise, because otherwise it's extremely tough to measure these signals. We have a third detector in Italy already, that's called Virgo. The only problem is it's a bit less sensitive. So it helps, but it's not, we can say, okay, we already have 3 gravitational wave detectors that can do everything these two can, unfortunately. Now there's another detector, Cagra, that's starting up. And so that should help in the future, that we have more detectors, because if you really want to then know where does the signal come from, that's similar to a GPS. You need several detectors to kind of point and localize the signal on the sky. If you only have 2, then your signal is kind of smeared out across a huge arch across the sky. And to really say, okay, it's in this region here, you need at least 3. And in the future, the hope is that if you maybe even have 4, there's another one, say, which is Indigo in India. Once we have more, then we'll get a much better sensitivity, and we'll know much clearer where the signals come from. And that will be very, very useful. Okay, so how do you measure this? I mean, what you really need to do is you need to measure distances to the accuracy of the size of a proton, even much less than that. And this sounds mind-boggling how you can do that. And so that's the detector. That's somehow, I mean, okay, these are interferometers, you have lasers bouncing back at a mirror, coming back, and then you merge them in your detector. And this is one of these mirrors, and then that's the mounting, how they're suspended. And what you have here is you have many of these suspension systems, each kind of reduces the oscillations, the noise from outside, vibrations, everything. to strongly shield these vibrations. If you wouldn't do that, there would be no way to measure anything, because anyone passing by any car would be so much bigger, the vibration from that, and the signal you want to see. Now they're done in a way that this laser signal here destructively interferes in the detector, and so whenever you kind of have say an effect, any either gravitational wave or vibration, then somehow you'll see actually laser light in your detector, and this way you kind of can already enhance the sensitivity, because typically this will be kind of very bright, very dark, the signal, and you won't see much, and you can have very sensitive detectors to see small changes from that. Right, and so here on the right-hand side, I mean, this is really weird how precise you have to do this. These different mirrors, they are mounted on, or say that's the mirror, these are kind of other masses, they're mounted on glass fibers, and they're so thin that if you would just touch this, they would immediately break. I mean, this is somehow a mass of kilograms, and they are mounted on really extremely thin glass fibers in order to reduce this noise, the noise and the vibrations from the surroundings. Okay, so how do you measure then the gravitational wave? And somehow that the idea is that you can only measure it due to all this noise if you know exactly what you're looking for. That's the only way. And so you're kind of really looking for the needle in the haystack. That the noise is the signal is completely swarmed in the noise. And only if you know what you're looking for and you search for a long time, then you can see that. And so what you need is something called a gravitational wave template. That's kind of the prediction of, well, how do the gravitational waves from such a merger, how do they look like? What's the signal in time? And you typically get this in a post-Newtonian expansion of this process. And so you then have a somewhat simple template, a function that you know. So a post-Newtonian expansion is an expansion in small velocities, v over c. And this gives you then what's called disturbed signal. So you get a template like this here. And, oh, okay, I can't play it. Okay, sorry, my button is gone. Maybe if I go out here. Okay, right. So that's, I mean, for the students who might not have heard this, that's how a neutron star merger sounds. Okay, and so they're in a kilohertz regime, so you can actually play them back, because that's basically sound frequencies. And as you can see in the neutron star merger, you kind of get for a long time a constant signal. If you've heard these black hole mergers, they're typically more dynamic. Neutron star merger only in the really end something dramatic happens, and for a long time you can have a signal that's roughly constant. And so the analysis, then comparing what you're looking for, your template with the data, is typically done by matched filtering. And the longer your template is, the better you can find the signal in that haystack. And correspondingly, the low frequency end of your frequency sensitivity range is very important, because initially you start with low frequencies, only in the end this goes up to kilohertz frequencies. And so the lower in frequency you can go, the longer in principle you can observe the signal, because as you can see, the signal amplitude does not change too dramatically here. So it's to some extent really frequency that limits things. And so for neutron star mergers, frequency is really important to have to go to low frequencies to more easily detect them, and to have a long template that you can compare and do this match filtering over a long time interval. Okay, so we heard a lot about this already today. We have one observation so far of an event where we have both, where we have the gravitational waves, and we also have all these electromagnetic signals. There were already talks, the gamma ray burst, an afterglow, and a kilonova. And I'll say a bit more about this later on. And okay, these are the corresponding chirp signals that you see in the detector for this event, GV 170817. And okay, you have the associated gamma bursts with these names. And well, they cover kind of the various stages of the event. I mean, first you have the merger, the gravitational wave signal before they even merge. Then you have the merger. That's what we don't see, unfortunately, so far, because the signal is very messy. I'll get to that. And then much later, you have these other optical emissions, and they typically stem from very distinct space and time regions, right? Much later, far further out from the initial merger region. And having all of them, even though the pointing so far was not ideal because we only basically had 2 detectors, allowed to localize where this event was, GV 170817, and they could associate it with this galaxy. So that was really nice that you have all these signals. You can learn much more than just with the gravitational waves. Okay, we already heard a lot about gamma ray bursts, so I think I can basically skip over that. The only thing I want to mention is that, you know, it's really hard to go from the initial merger phase to the gamma ray burst, and you know, there's a lot of modeling involved, very complicated processes going on, and people by now start to understand, or already since some time they understand how this can work. Because if you do the simulations, you really find that you create huge magnetic fields, and you get some jet-like structure here. So these magnetic fields can collimate charges, and so the goal is that at some point we want to describe the whole process, starting from the neutron star merger, and then model this, evolve, and in the end get us a signal. What electromagnetic probes can we detect from that? But obviously that's very hard. But right, these 2 events are obviously connected. The only problem is the connection is kind of tricky. And okay, I won't say too much more. Maybe only mention that because I think there wasn't much talk on this so far. There's this kilonova, and that typically happens far away from this merger region. I mean, it's much further out in space, in the ejecta of this process, and I'll say a bit more about this later on. Okay, and so I mean, this was really a nice thing that we could finally link this. I mean, gamma ray bursts have been observed for a long time, particularly short gamma ray bursts, and this way, having all these different signals simultaneously, you could really kind of see where they come from. So the kilonova is also extremely important for all of us, because what people understood is that they are kind of probably to large part what produce very heavy elements in the universe. And there's something called an R process. So that's a process here where you create one heavier and heavier nuclei. So this is the ordinary nuclei. That's the value of stability in the nuclear chart. And this is kind of, this process leads far away from this value of stability, and eventually then gets back and creates heavy elements like maybe gold, something like this. And due to this, you create a lot of energy in these nuclear reactions, and that heats the material there. Now, this R process only happens under special conditions that you can have in the ejecta of such a merger, namely sufficiently high temperature, sufficiently low densities, and so on. And but then again, these nuclear processes create energy, and that strongly heats these ejecta, and you get a strong signals, a strong basically another explosion. That's why it's called kilonova. It's 1,000 times bigger than an ordinary nova, and so you get a really bright isotropic source that you can also see over large distances. And so when you see the neutron star gravitational wave signal, typically one should also observe that. Right, and so what can we learn then from the actual, say, in spiral of these mergers? So as I said, they're different phases. The first phase is the in spiral. That's the signal we have. So we match that signal to the data, and what you typically find is that what this template mainly depends on is this. That's called a chirp mass. That's a particular combination of the masses of the two sources. Okay, and so to leading order, it just depends on that. This signal that I showed you, this template, this chirp that kind of increases in frequency and amplitude. And from this, you can very precisely, in particular for this event, the 700817, you can measure this chirp mass. They could measure it very precisely to this value. So you know kind of this combination, but what's hard then to get at is the individual masses. And the problem is that this is degenerate with other parameters, in particular with the spins of these progenitor stars. And so this is far more uncertain. And so this here is a plot of the two potential mass ranges of the two objects, M1, M2, in that particular event. And as you can see, well, yeah, it's basically degenerate along that line. And we don't really know where on that line we are. And to get to more clearly pin this down, you will have to go to much higher order in this post-Newtonian expansion, and that's much harder. So far there's still some uncertainty where they are. I mean, they're kind of around, say, 1.3 solar masses somewhere, but it could be a bit more asymmetric, that one of the stars is more massive and the other a bit lighter. So we just don't know this completely at this point. Another important thing that you can measure is how say, if you have this in spiral, you know, you already have tidal effect, just like the moon has on the Earth. And so these stars will already be distorted. And that will already happen, say, once they get close enough together, they will be distorted, and you can measure this. And that will be an imprint in that signal, in that chirp signal. These tidal effects will have an imprint, and they will slightly change it, and you can measure that. And so that is typically described by what's called a tidal deformability. That basically tells you how strongly you can somehow compress matter, how strongly you can change that star, squeeze it or stretch it. And it's typically given by a dimensionless parameter, the love number, and then other properties of these sources. And the problem, so this K2 is the quadrupolar love number. So this what this measures is quadrupolar tidal distortions, because only they can kind of emit gravitational waves. And so right, so the problem is what we find then is that the signal depends again on a particular combination of these tidal deformabilities, not individually, but on this combination here, involving masses and these two tidal deformabilities of the two stars. And even then, this only enters at rather high post-Newtonian order. And so the signal is kind of hard to detect, but they could measure that. And that's really important, because this directly then tells us something about the matter in these sources, right? It tells us how strongly can you compress stuff. And so typically for fast rotating sources, these effects would be more sensitive. And so this constrains then the equation of state, and that's shown here. So this is this, say, this parameter delta tilde, to combine tidal parameter, and Q is the mass ratio between these two stars. Okay, and well, then you can plot this. You can plot where in that plane is this, well, are these parameters most likely? These are kind of the dark areas. And as you see, I mean, you cannot say, okay, that's the tidal parameter, but we get a certain range where the tidal parameter should be, depending on, well, the range of the ratio of these masses. And say two different colors here are different scenarios on the spins. I told you that kind of the general, so you can either make a very conservative estimate what the spin is, namely it can be basically anything, or you can say, well, this neutron stars that we see, they don't spin arbitrarily fast, in particular in these, I mean, that's related to what we heard last week. Somehow, if you have accretion going on, then you can spin up a neutron star to large frequencies. But these stars in neutron star binaries, they typically cannot accrete from the companion, and so their their spins should be related to their, probably even to their birth spins, and so they cannot accrete much, cannot speed up. And so if you compare that to what you see in this, what we have seen from observation of these binary systems, and take these spins as a benchmark, then you can tighten it more and constrain it better. And well, these are these two. Say the red one is the low spins. This is less constraining. Okay, and so for reasonable assumption, you get a rather narrow range where that tidal parameter should be. Okay, so what can we learn then? Knowing that this gravitational wave signal actually tells us something about the matter inside. And so this is the same thing here now plotted, the same plot now plotted as a function of these two tidal parameters, tidal compressibilities. And again, you have a density plot that shows you where it's most likely. And what's shown here are certain equations of state. So these curves here are equations of state. And there are some that are very compatible with what we see, but there are others that are not at all. And so the signal already starts ruling out models of what a neutron star could be made of, and what the equation of state is in particular. I mean, how compressible, for instance, is that form of matter. Right, and so the lesson we kind of learn from that is that the equation of state cannot be too stiff. And that's interesting because we have another observation some years back already, that we have neutron stars heavier than 2 solar masses, right? And so the 2 solar mass constraint tells us the equation of state has to be sufficiently stiff. Otherwise, we wouldn't get a 2 solar mass star, and gravity would just shrink it, and it couldn't be stable and fall into a black hole. I mean, would form a black hole. Now, this gives us somehow another constraint, saying yes, but the equation of state cannot be too stiff either. So we are now kind of constraining the equation of state from 2 sides, and that's really, really useful. And taking that into account, taking all the astrophysical observations we have, doing a lot of modeling, some people have argued that, well, that already gives us some hints that maybe there's even quark matter in a neutron star. I mean, what they do is they plot various different parameters in the 3-dimensional plots, then they do all these different equation of states, and what you get for these parameters, and they find that, well, these parameters that we measured are more compatible with, well, they've kind of formed distinct, regions in this plot, and it seems that are more compatible if you have some form of quark matter inside. This all depends on assumptions, and it's all very early and hard. I mean, this game is really hard, but it's interesting. So this really tells us something new, having these tidal parameters. Okay, another thing that you might learn from that is, I think this was already mentioned, well, in a neutron star merger, you really probe the strong gravity regime, right? So you probe extremely large space-time curvatures. And in this case, I mean, we know that any physical theory should be invariant under general coordinate transformation. Einstein's theory is kind of the leading term that has this property, but there could be higher order terms. And when I say higher order, I mean somehow in an expansion in gradients or covariant derivatives. And in this case, if you go to higher order, there are many possibilities of such covariant theories. And there's, for instance, something called scalar tensor theories, there are F of R theories, and also in Istanbul, many people work on that. And that's extremely interesting because, well, it could be that this way we can detect effects beyond Einstein's theory. And neutron star mergers are the best laboratory for this because there you can have huge space-time curvatures. The problem is that this is very hard because you have these two different effects. You have effects from matter and you have effects from gravity. And, you know, we don't know much about the matter side. We don't know much about, here there are many possibilities what could happen. And to disentangle them is kind of hard. And therefore, so far in the future, this hopefully we can also constrain things even better there. Right now, it's really hard to say, okay, is this a matter effect or is this a gravity effect? And since we know that neutron stars, that there is matter, and we know that the matter is extremely important, the interactions are extremely important, otherwise we wouldn't even have the neutron stars we see. Well, maybe that's if we see something, maybe that's the more likely explanation. This is just a matter because we know it's there, it must be there, whereas we don't know if there are any effects beyond Einstein gravity. I mean, it could be that all these other terms are arbitrarily small. And some quantum gravity theories even predict that it could be very small. And so, yeah, right. I mean, it's hard to disentangle these two things. Okay, I think, how much time do I have left?
You're eating from the break, actually.
Okay, sorry. Okay, then I simply skip over the rest, I guess. Okay. So maybe we've seen another one. I just quickly want to mention this. Maybe we've seen another one by now, or people think this is another one. It's just not as clean as the other one. And the interesting thing is this new event that was in 2019 has a much higher chirp mass. That means much heavier masses. And this is interesting because, you know, I mean, so far we learned a lot about, I already mentioned it, about how you create very heavy neutron stars. And usually you wouldn't expect them in a neutron star binary system because they cannot accrete. And so either they were really born very heavy at birth, much heavier than all that we've seen so far, or something interesting happened. And so this is a really interesting event. We just don't really, I mean, we didn't see any GRB from that. We didn't see any electromagnetic signals. So it points towards the neutron star merger, because even if you would say, okay, one of them would be a black hole, that's equally hard or even harder to get that, to get such a, in this case, light black hole. And so this is a really interesting event, but so far it points to somehow a new formation channel for neutron stars. I mean, how you could create such a system, but otherwise it's puzzling. Okay, I think I then cannot go through most of the other stuff that I wanted to talk about, maybe dynamic effects. And I just quickly mentioned, you could either see them already in the in-spiral, say in the end of the in-spiral, you know, everything gets messy. And so whereas initially they're kind of tidally locked and things move up rather slowly, in the end, all this is so fast that you can excite oscillations in the stars, that you could have effects like the breaking of the crust, all kinds of events that can trigger dynamic processes in these stars. And you might be able to kind of see this in the signal. And these are all tiny effects. They only happen in the very end of the in-spiral, but there's a chance that eventually we'll see that. And okay, I'll have to skip over that. What I'm interested in is the post-merger phase. There you smash these stars. That means you turn them inside out, And the signal that you get actually comes from, well, that matter inside, not just from a surface. All the signals that you get initially come from there. And so the hope is that you can learn something about the matter itself. And it turns out that dissipation, for instance, could be very relevant for that. I mean, there could be strong dissipation on these very short time scales that you have in such a merger. And that's what we are currently working on, trying to figure out how important could that be, because that could strongly change the entire process in some sense. Because so far, the only energy sink is the gravitational waves that you emit, and eventually also neutrinos and other signals. And the gravitational waves, they carry away angular momentum. If you have dissipation in that merger product, you will turn it into heat. That means you will lose less angular momentum, and that heat will produce additional pressure. And that could strongly change the entire event, because it could stabilize it for a much longer period. And so there could be, if you take that into account, observable signals once we can see this gravitational wave signal. It's just very hard because it's very messy. The good thing is there are some characteristic peaks there, and so there could be a chance that in the hopefully near future, this merger phase will actually be observed. Right, so okay, I have to come to the end, so I will. Now, these mergers are kind of like falling stars. You have to be lucky, you see them, it's gone. Bryn will tell you about something else, namely doing kind of ordinary astronomy with ordinary sources that are just there and that you can see. And well, that's also very exciting. And okay, I stop here. I'm sorry for going over time.
No problem at all. Thank you very much for this very nice talk. But let me close the session so that we can have 10-minute break. There's one comment and another question on the chat panel. So I'd appreciate if you could take a look at some point. And we can meet at like, what time was that? Yeah, 3:15 to hear what Bryn has to say. All right, thanks.
Okay.